we've learned that the field lines around a positive source charge look like this. Why is this called a source charge? Because it produces the electric field, and I could test that electric field using a test charge. What if my source charge in the middle is negative? The field lines are the same, but now they point in, and the reason is because a positive test charge would be attracted to this negative source charge. What if we have more complicated scenarios, like one positive and one negative charge located near each other? Here's what the field lines look like. They exit positive just like before, and they enter negative just like before, but there's this curving that happens. Let's look back. See how these lines exit positive and then enter negative? We have the same thing happening, but now they curve around so that they complete the single line. So the lines curve around. If we flip the two and make the negative charge on the left side, we have the same picture, but the arrows point the other way, from positive to negative. But what if we have two positive charges or two negative charges? The field lines do something different. They curve away like this. Over here, the same thing happens, but now the field lines enter the negative charge instead of exiting the positive charge. To understand why this happens, we have to remember what these lines represent. They represent the electric field strength vectors. To understand these shapes better, we'll take the case of two positive charges. We want to test the field in the space around these two source charges. How do we test the field? We use a small positive test charge, and let's choose this point first. The positive test charge is really close to this one, so it's repelled with a strong force. And it's pretty far from this other source, so that positive test charge is repelled with a weaker force. We have to add these vectors together. And how do we add vectors? We move this tip to tail with the other. The vector sum is called the resultant, and it's tail to tail and tip to tip. Now let's test this point. We're a little bit farther away, so the positive test charge will be repelled with a weaker force. And that positive test charge is still pretty far from the other source, so that repulsion is weak. We want the net combined effect from the two, so we have to add these vectors together. And so those E vectors have a resultant that looks like this. And if we take one final point, we test the field here by placing a small positive test charge. And it's really far now from the first source, so that repulsive force is weaker. And it still is really far from this other one, so that repulsive force is weaker too. We want the net effect. These two forces per coulomb, we add them together, we sum them together to get the net. And the resultant is like this. What do we see? The field lines are kind of curving around the way the original picture showed. And we could do this at every single point, and we would get these types of lines that curve up and away. So now let's take another random location over here, and I want to know, what does the electric field strength look like here? Where does the electric field point at this location? Well, look back up top. Our rule is that the E vector is always tangent to the field line. So this E vector is tangent to the curved line at the point. At this point, the E vector in red is tangent to the line. At this point, the E vector is tangent to the curve. So down here, the E vector would have to be tangent to the curve. What about a different point? Right here. We use the same rule. We imagine a tangent line, and we make the E vector tangent to that field line. If we go back to a place where the line is not curved, this field line is straight, then it's the same old rule. The electric field strength, the E vector, is with the field line. Here's a practice question. If we place a positive charge right here at the top, where would the force be directed? Remember, the E vector points like this. and that E vector is tangent to the curve wherever the field lines bend. So if the E vector points this way, then that's where a positive charge would be pushed. They're in the same direction. But what if the question asked where a negative charge would be pushed? Well, the negative charge would be pushed tangent, but opposite the field line. Let's try that again down here. Where would a positive test charge be pushed if we placed it right here? Well, the E vector is always tangent and with the field lines. And what's our rule? Positive charges are pushed in the same direction as that E vector. If it asked about a negative charges are pushed opposite the E vector, against the field line.